We live in an era where we can 3D print houses and launch rockets into deep space. We like to think we've mastered the physical world. But if you look closer at the relics of our past, that confidence starts to fade. In the corners of our world, there are objects, monolithic stones and chemical fires that our modern labs simply cannot recreate. We have the blueprints, we have the lasers, but we've lost the how. Today, we're diving into 10 ancient artifacts that prove our ancestors weren't just ahead of their time. They were playing a game we don't even understand yet. Close your eyes for a second and imagine the Mediterranean Sea in the year 674. You are part of a massive invading fleet, hundreds of wooden ships strong, closing in on the Golden Horn of Constantinople. You have the numbers, you have the momentum. But as the Byzantine ships sail out to meet you, something impossible happens. From the bows of their vessels, a shimmering liquid is projected through large bronze tubes. It looks like water, but the moment it hits the air, it ignites with a roar that sounds like 1,000 lions. It strikes your ship, and the wood doesn't just burn, it erupts. You try to douse the flames with seawater, but the fire drinks the water. It grows brighter, hotter, spreading across the waves until the very ocean itself is a carpet of unquenchable flame. This isn't just a weapon, it's a nightmare. This was Greek fire. And 1,400 years later, we still don't know exactly how they did it. Greek fire was the Byzantine Empire's most closely guarded state secret. It was so classified that the recipe was never written down in full. It was whispered from emperor to successor, and only one family, the Kallinikos family, was entrusted with its manufacture. If you leaked the secret, it was believed you would be struck down by divine wrath. This security clearance worked so well that when the empire finally fell, the secret died with it. Now let's talk science. Modern researchers have spent decades trying to reverse engineer this lost napalm. We have three main puzzles: the chemistry, the ignition, and the delivery. First, the chemistry. Most modern theories suggest a base of crude oil or naphtha, mixed with resins to make it sticky. But naphtha alone doesn't explain why it burned better on water. Some scientists argued for quicklime, calcium oxide, which generates intense heat when it touches water. But quicklime doesn't spontaneously ignite oil. Others suggested sulfur or phosphorus. We can mix these today in a lab and we get something close, but it's either too thick to spray or too unstable to store on a wooden boat. Second, the ignition. This is where it gets truly weird. Many historical accounts claim the fire ignited spontaneously. In an era before matches or lighters, how did they start the fire at the tip of the nozzle without blowing up the entire ship? Some experts believe there was a pilot light at the end of the bronze tube, while others suggest a complex chemical reaction triggered by the impact with salt water. Imagine the level of molecular understanding required to create a hypergolic reaction, liquid that ignites on contact, using only 7th century materials. Third, the delivery system. This wasn't just a bucket of oil, it was a sophisticated thermal pneumatic machine. The Byzantines used a furnace to heat the liquid under pressure, a siphon pump to eject it, and a swivel-mounted bronze nozzle to aim it. Think about that. They had pressurized fluid mechanics in the Dark Ages. When modern engineers tried to recreate this for documentaries, they often found the pressure too low to reach the enemy, or so high that the bronze tanks exploded. Yet, records show the Byzantines used this for 500 years with surgical precision. In the 1930s and again in the early 2000s, chemists tried to brute force the recipe. They used high-tech sensors and chemical modeling. They produced modern Greek fire, but it lacked the roaring sound described in texts, and it didn't have the same buoyancy. Our modern versions are often too heavy. They sink and burn underwater, whereas the ancient version was said to float like a burning veil. This brings us to a humbling realization. We often view history as a straight line of progress, from dumb to smart. But Greek fire proves that technology can be a circle. We lost the how because we stopped needing it when gunpowder arrived. But in terms of pure chemical ingenuity, those Byzantine engineers were doing things with raw earth and fire that our billion-dollar laboratories still find commercially and technically difficult to replicate perfectly. We can split the atom, but we can't make the fire that saved Constantinople. We have the data, but we've lost the craftsmanship. It remains a ghost in the machinery of history, a reminder that once we were masters of a science that has now returned to the shadows. Welcome to one of the most remote places on Earth, Rapa Nui, or as most of the world knows it, Easter Island. Standing tall against the Pacific winds are nearly 1,000 silent sentinels, the Moai. For decades, the mystery wasn't just why they were built, but how they got there. Imagine a statue the height of a 3-story building, carved from a single piece of volcanic tuff, weighing as much as a fully loaded Boeing 737. Now, imagine moving that statue 11 miles across rugged, hilly terrain without a single horse, an ox, or even a wheel. In modern construction, we'd use a heavy-duty crane and a multi-axle trailer. The Rapa Nui people had nothing but stone tools and woven grass ropes. For years, the leading scientific theory was the roller hypothesis. Popularized by Thor Heyerdahl and later Jared Diamond, it suggested that the islanders cut down thousands of trees to use as wooden rollers. The story went that they destroyed their own ecosystem just to move these icons. It was a cautionary tale of ecological collapse. But there's a problem. Modern experiments using rollers are a disaster. To move an 80-ton Moai on rollers, you would need hundreds of people working in perfect synchronization, and the wooden logs would often crush under the immense pressure. Then, researchers noticed something strange about the statues left in the quarries versus those at the final sites. The statues in transit had a different base. They were leaning forward. When researchers asked the modern Rapa Nui descendants how their ancestors moved the giants, the answer was always the same. They walked. For a long time, scientists laughed. Statues don't walk. But in the early 21st century, a team of archaeologists decided to stop laughing and start testing. They discovered that the Moai were engineered with a low center of gravity. Their bellies were heavy, and their bases were D-shaped, not flat. This was a revelation. By using 3 teams of people with ropes, 1 at the back to stabilize and 2 at the sides to pull, the statue could be rocked back and forth. It literally shuffles forward. In a famous 2011 experiment, a 5-ton replica was moved 100 yards in under an hour using just 18 people. But here is where modern science hits a wall. A 5-ton replica is one thing. An 80-ton original like Paro, the largest Moai ever erected, is a different beast entirely. The physics of scale are brutal. As an object gets larger, its weight increases cubically, but the strength of the ropes and the friction of the ground only increase linearly. To walk an 80-ton Moai, the ropes would need to be thicker than a human thigh, and the tension required would likely snap any natural fiber. Furthermore, the walking motion on the island's steep, volcanic slopes would create such immense force at the heel of the statue that the volcanic tuff, which is actually quite soft, should have shattered or crumbled. Yet we see no shattered heels on the finished statues. This implies a level of force management that we still can't replicate with primitive materials. We can simulate it in a computer, sure. We can use high-tensile steel cables and hydraulic stabilizers to mimic the movement, but trying to do it with grass and manpower? We fail every time the scale gets real. And then there's the pukao, the massive red stone hats. These 10-ton cylinders were placed on top of heads that were already 30 feet in the air. How? Some suggest ramps, but the math for the incline required would mean ramps miles long. Others suggest parbuckling, rolling them up the statue's body. But one slip, 1 inch of misalignment, and the entire masterpiece is destroyed. The Moai aren't just art, they are a masterclass in static and dynamic physics. The Rapa Nui didn't just carve stone, they understood the soul of gravity. They knew exactly where the tipping point was. Today, we look at them and see mystery. But perhaps we should look at them and see a challenge. A challenge to a modern world that thinks complex means better. The Rapa Nui proved that with enough understanding of the Earth's natural laws, you can make the mountains walk. Perched 8,000 feet above sea level, hidden among the clouds of the Andes Mountains, lies Machu Picchu. It is the crown jewel of the Inca Empire. But if you look past the breathtaking vistas, you'll find a mystery written in stone. A mystery that modern stonemasons, even with diamond-tipped saws and laser levels, find nearly impossible to replicate. Look at the walls. These aren't just stacked rocks. This is ashlar masonry on a level of perfection that feels alien. Massive granite blocks, some weighing over 50 tons, are fitted together so tightly that you cannot slide a single human hair or even a razor blade between them. And here's the kicker. They use no mortar, no cement, nothing but the perfect fit of stone against stone. In modern construction, if we want to join two massive stones, we cut them into perfect rectangles. It's easy, it's logical. But the Inca, they chose the hard way. They used polygonal masonry. One stone might have 12, 13, or even 40 different angles, and the stone next carved to perfectly mirror every single one of those curves and corners. It's like a 3D jigsaw puzzle where every piece weighs as much as an elephant. For decades, historians said, oh, they just had a lot of time and a lot of patience. They just rubbed the stones together until they fit. But engineering-wise, that theory is falling apart. To rub a 20-ton stone against another to get a seamless fit would require more than just patience. It would require a way to lift, check, and lower that stone hundreds of times with sub-millimeter precision. How do you do that without cranes? How do you measure a complex multi-angled surface so perfectly that the final fit is airtight? Modern researchers have tried to replicate this using scribe and collapse methods, but they only succeed on a small scale with soft limestone. When you try it with the hard granite of the Andes, the tools break, the stones crack, and the seams are never as tight as the Inca originals. But the mystery goes deeper than just aesthetics. Machu Picchu is built on two fault lines. It's an earthquake zone. If these walls were held together by mortar, they would have crumbled centuries ago. Instead, the Inca engineered what we now call seismic dancing. Because the stones are not glued together, they are free to vibrate and move during a quake. They literally bounce in place and then fall back into their original, perfect alignment. The trapezoidal shape of the doors and windows further stabilizes the structure. Our modern skyscrapers use high-tech base isolators and hydraulic dampers to achieve this. The Inca achieved it using nothing but the geometry of raw rock. And then there's the Intihuatana, the hitching post of the sun. This is a single, massive boulder carved into a complex geometric shape that functions as an astronomical clock and calendar. The angles of the stone align perfectly with the winter solstice. Modern sculptors have noted that carving such precise angles into hard granite without leaving impact scars or tool marks is a feat of master craftsmanship. It looks as if the stone was softened, molded like clay, and then hardened back into granite. In 2026, we have CNC machines that can carve stone with incredible detail. But those machines require electricity, digital blueprints, and huge cooling systems. The Inca did this in the thin air of the mountains, using nothing but bronze chisels and river stones. Science is starting to admit that there's a missing technology here, perhaps a way of using vibration or a lost chemical process to soften stone that we haven't rediscovered. The takeaway? Machu Picchu isn't just a ruin. It's a message. It tells us that the Inca weren't primitive people working with rocks. They were master physicists who understood the earth, the stars, and the very vibration of matter. They didn't fight nature. They harmonized with it so perfectly that their work has outlasted the very empire that built it. In 1897, British soldiers entered the Kingdom of Benin in what is now modern-day Nigeria. They expected to find primitive artifacts. Instead, they were greeted by thousands of brass and bronze plaques and sculptures so sophisticated, so flawless, that the British Museum initially refused to believe they were made by Africans. They theorized that the Greeks or the Egyptians must have wandered into the jungle to teach them. They were wrong. What they found were the Benin bronzes, a masterclass in a technique called lost wax casting. Now, lost wax casting is something we still use today for jewelry and dental implants. But the scale and precision the Benin craftsmen achieved 500 years ago is what leaves modern metallurgists speechless. Think about the technical challenge. To create one of these plaques, you first have to carve a perfect model in wax. Then, you cover it in layers of fine clay. When the clay dries, you heat it, the wax melts out, hence the lost wax, and you pour molten bronze into the hollow shell. Here is where the impossible part starts. Bronze is a temperamental alloy. If the metal is too hot, it bubbles and ruins the detail. If it's too cool, it hardens before it reaches the tiny crevices of the mold. The Benin bronzes are incredibly thin, sometimes just a few millimeters thick, yet they cover massive surface areas without a single crack, bubble, or flaw. In a modern foundry, achieving this level of thin wall casting requires vacuum chambers and pressurized injection. The Benin masters did it in open-air pits, using nothing but charcoal and hand bellows. When scientists analyzed the chemical composition of these artifacts, the mystery deepened. They aren't just bronze. They are complex alloys of copper, tin, and lead, often with trace elements that act as fluxes to help the metal flow better. The ratios are so precise that it suggests the Edo people had a deep empirical knowledge of chemistry, knowledge that was passed down through guilds for centuries. But it's not just about the metal, it's about the undercuts. Look at the detail on the warrior's armor, the tiny links of chainmail, the pupils of the eyes. Many of these features are undercut, meaning they curve inward in a way that should make it impossible to remove a clay mold without breaking the sculpture. This implies they were using multi-part sacrificial molds or a material science for their clay that we haven't fully decoded. In the 20th century, several world-class artists and foundries tried to create perfect replicas of the Benin bronzes. While they could make something that looked similar, they couldn't match the structural integrity or the patina, the chemical skin of the metal, that the originals possessed. Our modern versions often feel sterile or brittle compared to the 16th century originals. The Benin bronzes are more than just museum pieces. They are metal records of a lost science. Every plaque tells a story of a court, a battle, or a king. But to a scientist, they tell a story of a civilization that had mastered the transition from liquid to solid, from fire to art, with a grace that our digital age still struggles to grasp. We often talk about the Industrial Revolution as if it were the beginning of high-tech manufacturing. But looking at these bronzes, you realize that a different kind of revolution happened in the forests of West Africa. One where the laboratory was the forge and the computer was the craftsman's intuition. And that is a technology we are still trying to relearn. We often think of construction as a process of addition. You take bricks, steel, and glass, and you pile them up until you have a skyscraper. But at the Ellora Caves in Maharashtra, India, there's a structure that defies every rule of modern civil engineering. It's the Kailasa Temple. And it wasn't built, it was excavated. Imagine a solid basalt cliffside. Now, imagine carving a cathedral out of it, starting from the top and working your way down to the floor. No scaffolding, no room for error, and no way to put a piece back if you chip it off by mistake. Modern estimates suggest that over 200,000 tons of solid volcanic rock were removed to create this masterpiece. To put that in perspective, that's equivalent to the weight of 2 Nimitz-class aircraft carriers. Archaeologists tell us it was completed in less than 20 years. Do the math. That means the workers had to remove roughly 60 tons of rock every single day, working around the clock. Even today, using heavy-duty excavators, dynamite, and diamond cutters, we would struggle to meet that deadline without compromising the structural integrity of the basalt. But here is the real scientific headache: the negative space problem. When you build a house, you have a blueprint for where things go. When you carve Kailasa, you need a blueprint for what isn't there. The architects had to visualize every pillar, every ornate elephant carving, and every 3-story gallery inside a solid block of stone before they even touched a chisel. Modern engineering firms have looked at Kailasa and concluded that if we tried this today with 21st century machinery, the vibrations from our drills and jackhammers would likely cause microfractures throughout the basalt. These fractures would lead to the entire structure collapsing under its own weight. Yet, 1,200 years later, Kailasa stands perfectly intact, without a single structural crack. This implies that the ancient carvers used a method of vibration-free stone removal that we simply don't possess. Then, there's the mystery of the missing debris. Where did those 200,000 tons of rock go? Usually, near ancient sites we find massive mounds of rubble or tailings, but around Kailasa, the debris is nowhere to be found. It's as if the stone wasn't just chipped away. It was dissolved or transported by a logistic system we haven't discovered yet. Inside the temple, the complexity increases. There are bridge-like structures connecting the different galleries, all carved from that same original monolith. There are drainage systems, rainwater harvesting tanks, and intricate tunnels, all hidden within the design. To plan the plumbing of a building while you are carving it from the roof down is a feat of spatial mathematics that should be impossible for a primitive society. Some theorists suggest they used lost sonic technology, using sound frequencies to soften the rock or break it along precise lines. While that sounds like science fiction, modern science is actually exploring ultrasonic machining today. The irony? Our ultrasonic tools can barely carve a small industrial part. These people carved a 100-foot-tall temple. Kailasa is a reminder that our ancestors weren't just stronger or more patient. They had a different relationship with the physical world. They didn't see a mountain as an obstacle. They saw it as a statue waiting to be revealed. It remains the world's largest monolithic structure. A 7th-century miracle that makes our modern steel and glass towers look like temporary toys. When we think of ancient Egypt, we usually think of the pyramids. But there's something even more baffling hidden in plain sight: the Colossi of Memnon and the statues of Amenhotep III. These aren't just big. They are made of quartzite. On the Mohs scale of mineral hardness, a diamond is a 10. Steel is around a 5 or 6. Quartzite, it's a 7. It is one of the hardest, most stubborn rocks on the planet. To carve it today, we use diamond-tipped industrial saws and high-pressure water jets. Yet, the Egyptians were shaping this stone 3,400 years ago into faces with perfect symmetry and skin as smooth as silk. Let's look at the math. The Colossi of Memnon weigh about 720 tons each. They weren't carved where they stand. They were transported 420 miles overland from a quarry near Cairo. Think about that, 720 tons, moving across the desert without an internal combustion engine. But the real impossible part isn't the transport, it's the surface finish. If you take a bronze chisel, the tool we are told the Egyptians used, and strike quartzite, the chisel will bend or shatter. It's like trying to cut a steak with a plastic spoon. Some historians suggest they used sand and friction, rubbing the stone for decades. But look at the inner corners of the statues, the nostrils, the eyes, the hieroglyphs carved into the back. These are deep, precise cuts with a constant width. In modern engineering, we call this a feed rate. When engineers examine these cuts under a microscope, they find something shocking. The spiral grooves left in the stone suggest that whatever tool was used was penetrating the quartzite at a rate of 2 millimeters per revolution of a drill. To put that in perspective, a modern diamond drill usually struggles to achieve that same speed. This implies the Egyptians had a power source or a mechanical advantage that allowed them to exert thousands of pounds of pressure with incredible rotational speed. But where are the machines? Why haven't we found a power drill of the pharaohs? This is where science gets uncomfortable. Some researchers, like Christopher Dunn, argue that the Egyptians used ultrasonic machining. This involves vibrating a tool at thousands of cycles per second, turning the hard stone into dust. It explains the lack of impact marks. It explains why the surfaces are so perfectly flat they can be measured with modern precision flat gauges. Look at the Serapeum of Saqqara. Inside this dark underground tunnel are dozens of granite and quartzite boxes weighing up to 100 tons. The interior corners are so sharp and the surfaces so flat that they deviate by less than 1,000th of an inch. We struggle to do this today with CNC machines in a temperature-controlled factory. The Egyptians did it in a torch-lit tunnel. Even more baffling is the hardness paradox. we find quartzite statues that have been polished to a mirror shine. To polish quartzite, you need an abrasive that is harder than the stone itself, like diamond dust. Where did they get it? And how did they apply it so evenly that the statue reflects light like a piece of glass? Science today is still trying to catch up. We can't explain how they maintained symmetry across a 60-foot statue. We can't explain the drill marks. And we certainly can't explain why they chose the hardest materials possible when easier stones like limestone were everywhere. The Egyptian master masons weren't just laborers. They were materials scientists. They knew something about the molecular structure of stone and how to overcome its resistance that we have lost in our transition to mass production. They didn't just build monuments. They left us a riddle in quartzite that 3,000 years of rain and sand haven't been able to erase. We often think of ancient timekeeping as something primitive, a shadow moving across a circle of stones. We think of it as close enough. But for the ancient Egyptians, close enough was an insult to the gods. They didn't just want to know the hour, they wanted to map the heartbeat of the universe. In the Valley of the Kings, archaeologists discovered a sundial dating back to the 13th century BC. At first glance, it looks like a simple limestone slab with a semicircle and 12 segments. But when modern astronomers and mathematicians put it under the lens, they realized they weren't looking at a clock. They were looking at a masterpiece of spherical geometry. Here's the problem modern science faces when trying to reproduce this: the Earth's tilt. Because the Earth is tilted on its axis, the path of the sun changes every single day. An hour in midsummer is physically longer in terms of daylight than an hour in midwinter. Most ancient civilizations just accepted this error, but not the Egyptians. Their sundials were engineered to account for unequal hours. They calculated the precise angles needed so that the shadow would provide a consistent measurement of time, regardless of the season. To do this today, you would need a solid grasp of trigonometry and calculus. You would need to understand the Earth's obliquity. Yet, the Egyptians were doing this 1,000 years before the Greeks even invented formal geometry. But the real mystery lies in the portable sundials. The Egyptians had pocket-sized timekeepers that functioned across different latitudes. Think about the engineering required for that. If you move 100 miles north or south, the angle of the sun changes. A fixed sundial becomes useless. But these ancient devices had adjustable scales. Modern engineers at companies like Rolex or Patek Philippe spend millions of dollars on R&D to create mechanical complications that track celestial movements. The Egyptians achieved this with a piece of ivory, a plumb bob, and a mathematical formula that we still haven't fully decoded. When we try to 3D print these dials today based on ancient blueprints, they often don't work. Why? Because we are missing the calibration constants, the secret numbers the Egyptians used to bridge the gap between the flat surface of the dial and the curved path of the sun. And then there's the precision of the carving. The lines on these dials are often less than a millimeter wide, carved into hard stone. If a line is off by even a fraction of a degree, the clock loses minutes every day. Over a month, it would be useless. Yet, these artifacts show an accuracy that rivals modern quartz movements in terms of solar tracking. Some researchers believe the Egyptians didn't just use the sun, they used water clocks, or clepsydras, to calibrate their sundials at night. These water clocks used a tapering vessel to ensure that as the water level dropped and the pressure decreased, the flow remained constant. That is Fluid Dynamics 101. To manufacture a vessel with that exact internal curve requires a mathematical function that wasn't officially discovered until centuries later. Science today struggles to explain how a civilization, with telescopes, without digital computers, and without advanced glass lenses, could map the sky with such precision that their timekeeping devices are still accurate to this day. We can build an atomic clock that won't lose a second in a billion years, but we need a laboratory and a power grid to run it. The Egyptians did it with stone and shadow. They didn't just live in time, they understood it as a dimension of the cosmos. Their sundials aren't just artifacts, They are silent witnesses to a level of astronomical science that we are only beginning to appreciate. It makes you wonder, if they were this precise with their shadows, what else were they measuring that we've completely missed? In the middle of the vast Pacific Ocean, on the remote island of Pohnpei, lies a city that shouldn't exist. It's called Madol. It is a sprawling complex of 92 artificial islands built directly on top of a living coral reef. While Venice is famous for its wooden piles, Madol is constructed entirely of stone. Specifically, massive columns of naturally formed basalt. We are talking about a total weight of approximately 750,000 tons. To give you an idea of the scale, that is more stone than was used to build the Great Pyramid of Giza. But the Egyptians had the Nile River and thousands of workers. Madol was built by a small island population on a reef surrounded by deep ocean. The first thing that baffles modern science is the source of the stone. The basalt columns, some weighing up to 50 tons and reaching 20 feet in length, came from the other side of the island. There are no roads, no wide paths through the dense jungle, and certainly no cranes. But more importantly, the stone had to be transported across the water. In the 1990s, a team of engineers attempted to replicate the transport of a single 5-ton basalt column. They built a massive wooden raft, tied the stone down, and tried to float it to the reef. The result, the raft flipped, the stone sank, and the engineers barely escaped. If a 5-ton stone is impossible for modern researchers with nylon ropes and calculated buoyancy, how did the ancients move 50-ton blocks across the waves without sinking their entire fleet? Local legend says the stones flew through the air, moved by the spells of twin sorcerers. While science looks for a more grounded explanation, we are coming up empty. To move 750,000 tons of rock onto a reef, you would need a continuous conveyor belt of ships and labor for centuries. Yet, archaeological evidence suggests the main structures were raised in a relatively short period. Then there is the wet construction problem. Unlike Machu Picchu, which sits on solid ground, Madol is built in the intertidal zone. The workers were fighting the tides. Every pillar had to be placed with precision while waves crashed around them, and the ground beneath them, the coral, was shifting. How do you stack 50-ton logs of stone in a lattice pattern, underwater or in mud, so perfectly that they remain stable for 1,000 years against Pacific typhoons? Modern marine architects have analyzed the layout of the canals. They realize that Madol isn't just a city, it's a sophisticated hydro-engineering project. The canals were designed to flush out waste with the tides and protect the inner sanctums from storm surges. The level of fluid dynamics understood by these primitive islanders is staggering. They essentially turned a chaotic reef into a calibrated machine for living. Even today, we struggle to build on coral. Most modern resorts built on reefs require massive concrete pilings, steel reinforcements, and constant maintenance against saltwater erosion. Madol has no mortar, no steel, and no concrete. It is held together by pure gravity and the sheer genius of its geometry. When you stand among the ruins of the Kailasa Temple, with walls 25 feet high, you realize that we aren't just looking at stacked rocks. We are looking at a lost branch of maritime engineering. A science that understood how to use the ocean's buoyancy, the reef's structure, and the stone's weight in a way that we have completely forgotten. Madol remains the only ancient city ever built on a coral reef. It is a silent monument to a civilization that conquered the sea using the very bones of the earth, a feat that modern science can simulate in a computer, but can't seem to replicate in the real crashing waves of the Pacific. For centuries, local fishermen at Lake Nemi near Rome told stories of giant ghost ships resting at the bottom of the lake. People laughed. They said it was impossible. Why would the Romans build massive ships on a tiny volcanic lake, only 1.5 miles wide? But in 1929, when the lake was drained, the world fell silent. 2 colossal vessels emerged from the mud, each over 230 feet long. These weren't just boats, they were floating palaces, and the technology found inside them shattered our understanding of ancient history. The first thing that shocked modern naval architects was the mortise and tenon joinery. Today, we use nails, bolts, and industrial glue. The Romans fitted thousands of wooden planks together using hand-carved joints, so tight they were practically watertight, even without sealant. But they didn't stop there. To protect the hull from organisms, they wrapped the entire ship in lead sheeting, fastened with copper nails and a layer of wool soaked in resin. This is a multi-layered protection system we didn't reinvent for steel ships until the 18th century. But the real impossible artifacts were found inside the machinery. Archaeologists discovered a set of bronze ball bearings. Before this discovery, we believed the ball bearing was a modern invention by Leonardo da Vinci or the engineers of the Industrial Revolution. Yet, here they were, 2,000-year-old bronze spheres designed to support a rotating platform, likely for a statue or a crane. The precision required to cast these spheres so they would rotate smoothly is a level of metallurgy that modern science struggles to explain without the use of precision lathes. And it gets deeper. The Nemi ships had plumbing. We found bronze valves and lead pipes that supplied constant running water to the cabins. These weren't just gravity-fed, they used sophisticated piston pumps to move water upward. They even had a hypocaust system, central heating, where hot air was circulated through pipes under the marble floors to keep the emperor's feet warm in winter. In the 1990s, a team of researchers tried to build a full-scale replica of the Nemi hull using traditional Roman methods. They quickly realized the logistics were a nightmare. The sheer amount of seasoned oak, the millions of hand-carved joints, and the precision of the lead lining made the project so expensive and labor-intensive that it was deemed commercially impossible for any modern shipyard without massive government funding. The Nemi ships prove that Roman naval engineering was a peak that we descended from. After the fall of Rome, the knowledge of ball bearings, complex plumbing, and large-scale hull protection was lost for over 1,000 years. We didn't surpass them until the age of steam. Today, we use CAD software to design ships and robotic arms to weld them. But the Nemi ships were designed with a living geometry, a way of shaping wood and metal to withstand the pressures of water and the weight of marble palaces, all calculated by hand. They remind us that progress isn't always a straight line. Sometimes a civilization reaches a height so great that when it falls, the world forgets what it was even capable of. The Nemi ships were high-tech masterpieces in a low-tech world, and we are still finding their blueprints in the mud of history. For our final mystery, we travel to the arid plateaus of southern Peru. From the ground, it looks like nothing more than a series of random paths in the dirt. But the moment you rise 1,000 feet into the air, the desert floor transforms into a colossal sketchbook. These are the Nazca lines. Spanning over 190 square miles, these geoglyphs depict animals, plants, and perfect geometric shapes. Some, like the famous monkey or the spider, are over 300 feet long. Others are straight lines that run for miles, crossing deep gullies and climbing steep hills without ever deviating by even a fraction of a degree. Modern science faces a massive scaling paradox here. If you want to draw a small circle on a piece of paper, it's easy. If you want to draw a circle 500 feet wide on uneven desert terrain, every tiny mistake at the start becomes a massive error at the finish. In modern surveying, we use laser theodolites and GPS coordinates to ensure a line stays straight over long distances. The Nazca people had none of that. For years, researchers thought they used a grid system with wooden stakes and strings. But here's where the math gets impossible. Many of these figures are single-line drawings. The entire hummingbird, for example, is made of one continuous path that never crosses itself. To plan a continuous path on such a massive scale, where the artist cannot even see what they are drawing, requires a level of advanced spatial mathematics and pre-planning that we usually associate with computer-aided design. In the late 20th century, a team of German researchers tried to recreate a large figure using only ancient tools. They found that even with dozens of people and long ropes, they couldn't maintain the perfect curves and proportions seen in the originals. Their lines were jagged. The Nazca lines are fluid, as if drawn by a giant pen from the sky. But the real insight isn't the art, it's the engineering of longevity. The Nazca Desert is one of the driest places on Earth, but it's not windless. Usually dust and sand would cover these shallow trenches within years. However, the Nazca people understood the local microclimate. By removing the dark, iron oxide-coated pebbles to reveal the lighter sand beneath, and then carefully piling those pebbles along the edges, they created a windbreak system. This system creates a layer of still air at the bottom of the trench that prevents erosion. Think about that. They didn't just draw on the ground, they engineered a self-maintaining atmospheric shield for their art. Science still struggles to model this boundary layer effect perfectly for modern desert structures, yet the Nazca lines have survived for 2,000 years. Then there is the hydraulic mystery. Recent satellite imaging has revealed that many of the lines align perfectly with underground aquifers. Some researchers argue that the lines weren't art at all, but a massive, coded map for a hidden water system. This implies that the Nazca had a way of seeing underground, perhaps through advanced dowsing or geological observation that we haven't fully validated yet. We look at the Nazca lines and ask, who were they for? Because we assume that since they can only be seen from the sky, the builders must have had flight. But perhaps the real question is, what did they know that we don't? The Nazca lines prove that our ancestors could master the big picture without ever leaving the ground. They could project a complex image from their minds onto the surface of the earth with a precision that our best surveyors still find humbling. In an age where we rely on satellites to tell us where we are, the Nazca people remind us that the human mind, equipped with nothing but geometry and observation, can create something so perfect that even time itself refuses to erase it. After looking at these 10 wonders, we're left with a humbling realization. Our modern world is built on the philosophy of efficiency and replaceability. We build things to last 50 years. They built things to last forever. We rely on external power. They relied on internal mastery. The fact that we cannot reproduce Greek fire or walk an 80-ton Moai doesn't mean our ancestors were aliens or magicians. It means they spoke a language of science that we've simply forgotten. They understood the vibration of stone, the behavior of fluid under pressure, and the geometry of the stars without needing a single microchip. As we move deeper into the age of AI and digital complexity, these artifacts stand as a silent challenge. They remind us that true advancement isn't just about how fast we can innovate, but how deeply we understand the world we live in. Ancient science isn't primitive. It's a different path of human genius. Perhaps the next great breakthrough in our technology won't come from looking forward, but from finally learning how to read the secrets left behind in the stone.